Greetings everyone. In the previous video, I discussed briefly about the AVR architecture and demonstrated some assembly instructions for it. In today's video, I will discuss some more assembly instructions and later I will do an exercise in the physical ATmega32 device. So the first instruction for today is the in instruction. What it does is it loads a register, a general purpose register with the content of an IO register. So it is also a 2-byte instruction. 5 bits are used as the opcode and 5 bits are used to represent the general purpose register, and the other 6 bits are used to represent the IO register. We can only access first 64 IO registers with the in instruction. So the next instruction is out. It stores the content of a general purpose register to an IO register. Like the in instruction, it can access first 64 IO registers, and it can access the all 32 general purpose registers. So here are the IO registers with their memory address and IO address. So an important thing to notice here is the IO address starts from 00. Here you can see the first address of TWBR register is 00 and the memory address is 20. In the in and out instruction, the IO address is indicated. That means we are accessing the IO address, not the actual memory address. So the next instruction is jump instruction. It's also called unconditional jump. So the K value, the K operand here represents a tag which indicates a specific part of the code base. Normally, the code executes sequentially, but if you want to branch out to some other part of the code base, we can use the jump instruction. So here 22 bits are used to represent a tag name. We will show the jump instruction in an example later. So an important register in the CPU is called the program counter. The program counter addresses the instruction to be executed next. Initially, when the microcontroller powers up, the initial address is 0000 and the program counter is loaded with the next address to be executed. It indicates the program memory, of course. For ATmega32, the program counter register is 14 bits. In the AVR architecture, the program counter can be of highest 22 bits. Another important register is the status register, also known as SREG. It shows the various flags for ALU operations. Also, it has 2 enable bits, that is T and I, and other 6 bits represent various flags. For example, the latest arithmetic and logic unit operation results to 0. In that case, the 0 flag will be 1, else it will be 0. Similarly, if the latest operation in the ALU is negative, the negative flag will be 1. Similarly, if the operation has a carry, the carry flag will be turned into 1, and else it will be 0. We will discuss all of this in next. We will discuss conditional branch instructions and looping. It will be based on the flags we discussed previously. So I have created a new project in Microchip Studio for AVR, and let's demonstrate the conditional branch statements. So here I have written a small program to demonstrate the BRNE condition, that is branch if not equal instruction. So how it works is, if the latest result in the ALU is equal to 0, then the instruction falls through. The program counter falls through. Then the next instruction is executed, and if the result in the ALU is not equal to 0, then it branches, and as we're saying it to branch in L1, it goes back here and this instruction gets executed. The DEC R16 represents to decrement the value of R16 by 1. Let me build the project first, and then we will debug it. So this is the I/O window. Here we can visualize the I/O registers. You can go to debug, then Windows, and then if you, that's how you can put the I/O screen in front. So let us create a breakpoint here, and then we'll start executing the program. So first we will visualize the R16 register. The address for R16 is 10 in hex. So we'll look into this content. So if we step into the instruction, you can see the value in 10 gets 4. After that, it enters the L1 loop, then decrement instruction gets executed and it becomes 3. Then in the BRNE L1 instruction, it checks whether the result in the ALU, that is the result of R16, because the last instruction was R16, decrement R16. So in the ALU, R16 register's value is stored in the result of ALU, result register of the ALU. So it checks that R16, the latest ALU result, is not 0. So that's why it branches. That means it goes here. Then it gets decremented by 1, and R16 becomes 2, and again it goes back to L1. Then it gets 1, goes back to L1. Now it gets 0, and you will see it will not branch this time, it will fall through. So it gets to this instruction NOP. NOP is just time wasting operation. So the opposite of BRNE operation is BREQ operation. So this will branch if the latest result in ALU is 0. If it's not 0, then it will fall through. Similarly, we have other instructions for other flags, like the carry flag, the overflow flag, and half carry flag, etc. We'll look into them later. So the next topic is preprocessor derivatives. These preprocessor derivatives actually are instructions for the compiler. These are not statements. That means these lines will not be executed by the machine. These are instructions for the compiler. The include macro is used to include other files into the program. It's similar to hash include in C. The .org represents the starting memory address of this program, and .equ is similar to define in C. So when we use malloc later in the program, it will be replaced by 0x300. Let's talk about the stack and stack pointer. In the RAM memory of a microcontroller, we need to allocate a specific space for the stack memory. The stack memory is used to store both data and addresses. Two registers are used to represent the stack pointer. So if you are familiar with the data structure stack, it will help you understand it more. There are two parts of the stack pointer, SPH and SPL. The SPL indicates the lower byte and SPH indicates the higher byte. To use the stack in a program, first we need to initialize the stack pointer. Generally, it's common to initiate the stack pointer the highest RAM value. Some operations of stack is push and pop. So if some data is pushed in the stack pointer gets decreased by some number. That means it begins at the highest level, and then if we push some data, the data will be stored in the current stack pointer address, and then the stack pointer will be decremented by 1. If we push another data, it will first store the data into the stack pointer address, and then it will get decremented by 1. And if we pop some data, it will increase the stack pointer value. So stack is used to call subroutines. Subroutines are similar to functions. We will see in the next slide what a subroutine is.